My name is Haley Snyder, and my project was on the estimation of silica, carbonate, and other clay mineral content by FTIR spectroscopy in mud-rich sediments and its implications for sediment provenance analysis. I worked with Dr. Edgardo Pujols and Dr. Oscar Shin at Lamar University, my home university. It was a big privilege and honor to do that. That is a big title, and it is long, and for some of you it makes no sense, so I did this. There we go. Plain English. Use infrared light to identify minerals in sandy rocks with mud-sized grains to uncover the history of the sandy rocks. Is that better? Yes, much better. So basically the motivation for our study was to use fine-grained particles because they can yield crucial insights into understanding the depositional processes involved in mud-rich sedimentary systems and also reconstruct the depositional history of those rocks. So our goals were to combine the previous sandstone petrographic analysis with FTIR, or infrared spectroscopy analysis. FTIR means Fourier transform infrared spectroscopy. There you go. That's a big word, I know. But the sample to your top right, that is one of the samples that I used. It is a picture of the sample under thin section. For standard petrographic analysis, what you do is you use that, you do point counts, you count the number of mineral grains that you see, and then you take a percentage of those minerals to the total mineral grains in the sample. The sample to your left, that is called a QFL chart. That is what you use when you do the point counts. You put this on a QFL chart, which means quartz, feldspars, lithics, and it compares the percentages of the quartz to the feldspars to the lithics, and then you can find provenance or sourcing from these charts. Very useful. And then the chart to your bottom right, that is a typical Spectra chart of, and that's actually of the sample that I ran, one of the samples. So I wanted to combine these two methods because I wanted to see, we wanted to get further insights into the fine grains in the samples because it can tell us how the role of basement involved uplift and how it affected sediment composition, sediment dispersal patterns, and also in the Cordilleran Foreland Basin, which is a very important basin. It's a very popular basin. So this is actually an example of, during this time, going from the Cordilleran Foreland Basin as the Farallon Plate was subducting and the shallow subduction to the late stage shallow subduction. All right, and I'm sorry I have to rush through because I'm spending too much time on these first ones. So this is a Nicolette IS-50 FTIR-ATR spectrometer, and combined with the QFL chart. And so this is what I was wanting to use to do my provenance analysis. This is a reconstruction of sediment dispersal patterns, a proposed reconstruction in the Cordilleran Foreland Basin. This is part of, well, one of my goals was to improve source to sink reconstructions, and this is one of the reconstructions, the proposed reconstructions. I also wanted to see, to determine thick skin deformation, if it was active and influencing during the late Campanian sedimentation north of the Uintas and rock spring segments of the Cordilleran Foreland Basin. So, how I used this mid-infrared light spectrum to analyze the rock samples, I wanted it to use it as a complement to the standard petrographic analysis in mud-rich sandstones. There has been prior studies done in clay stones, which are basically all fine-grained, very mud-sized grains in the rocks. But I wanted to apply it to, of course, their fine sandstones, the mud in those, in the coarser fine sandstones. And the way to do that is first to run, of course, the spectra, get the spectra, identify the minerals in the spectra, and this one right there is quartz. So there is quartz in that sample, but also to quantify how much of the minerals are in that sample as well, because that, and when you compare that to the QFL charts, that would offer some more insight, see how accurate we are getting to the larger size grains in the sandstone to the ones that you can't see under thin section. QFL plots, as I explained earlier, it compares the quartz concentration to the feldspar and lithic concentrations in the sandstone samples. Our geologic setting is in the Colloquium Basin. This is Rock Springs, Wyoming. SRAL2 from the Almond Formation near the Rock Springs uplift. TM and TC401 are near the Sandwash Basin. TM401, TC401 are from the Williams Fork Formation. And as I said earlier, SRAL2 and SRAL3 are from the Almond Formation, which is coastal plain deposits and shore face in origin near the Western Interior Seaway. TC401 are samples that are mostly coastal plain deposits. All right, so my methodology. As I explained earlier, when I ran the spectra and I analyzed the spectra, I needed to identify the peaks that are unique to certain minerals. And then I used a 5-mineral standard, which was quartz, calcite, plagioclase, K-feldspar group, and biotite. And then I wanted to quantify the minerals in the samples using the calibration curve. The calibration curve is based off Beer's law, which compares absorbance to concentration, and it's a direct relation, so you can get a curve off of that, and it's a very useful tool that we use. So, how do you do this? Well, you make a potassium chloride pellet. What you do is you take your sample, and the benefit of this, you get to use a very small piece of your sample because it's like 0.0005 grams of your sample. And so you grind up a piece of your sample, then you homogenize it with KCl or potassium chloride in a mortar and pestle. Then you vacuum press it for 15 minutes and load it onto this little apparatus, and then you put it into your FTIR to run infrared light through it, and then you get this. So these were my 5 minerals that I ran, and the bars in blue, this is the identifying spectra, or the identifying peaks of those certain minerals. And the way that this works is like, let's take calcite for example. It excites the double bonded carbon-oxygen bond, and at that point, there is a peak, and a very large peak. And so that is a carbon-oxygen double bond at 1425, and that is the way that I was able to identify the peaks in the sample. So I took that's where I identified the bars in blue, and those are the peaks that we got in the minerals. Now, to identify the minerals in the sample, this is the spectra from SRAL2, and in black, that is the spectra of the samples. And the colored spectra is the spectra of the minerals in the sample. Let me say that first. And so here's quartz again, and so we have our quartz highlighted in blue, and the quartz spectra is in green with the bar highlighted in blue. And then right there you can see where SRAL2 has that peak at around 1083, and that is a pretty large peak for the sample, and so that is how we identified quartz in the sample. So the standard petrographic results were pretty typical of a recycled orogenic material, and so all of them fell into that top part of the QFL chart, which was to be expected. So FTIR analysis is standard petrographic analysis. So this is where we're combining the two analyses. So, which was really interesting because, yes, they were very consistent with each other. The FTIR analysis, the spectra, the minerals that I got compared their spectra with the QFL chart were very consistent, but we did see something really interesting. There is an OH peak in the sample at 3419, which indicates possible phyllosilicate or amphibole mineral groups. So that was really cool. The geologic implications of this are really good because the FTIR results were able to reveal the presence of felsic minerals and arcosic sands. This is something that the QFL charts, as far as the felsic igneous minerals, it did not pick up. This indicates sediment sourcing from the Uinta's basement uplift and also recycled orogenic sediments from the severe fold and thrust belt. The sedimentary compositional and morphological analysis, it showed no distinct association between the samples, and the basement core uplift in the Uintas or rock springs, which is very important to mention because, as I said earlier, the standard petrographic analysis did not note the presence of amphiboles or phyllosilicates, so that's very important to note. The sediment provenance results in the QFL chart show the samples from the rock spring vicinity were mainly recycled orogenic material. So the qualitative analysis on the Almond and Women's Fork formation showed similar compositions to one another. Also, plagioclase and K-feldspar groups, just letting you know, they are very hard to tell the difference between the two, and they're very similar in the IR spectra. So that was one thing that we found that was a little challenging. Also, quartz and feldspar tend to dominate in the sample spectra, and the OH bond, as I said earlier, it indicates the presence of mineral groups common to felsic rocks, which indicates sediment sourcing from the Uintas basement. The standard petrographic analysis missed these possible mineral groups. So, I was not able to do the quantification because I ran into some issues where I could not exactly get precise percentages out whenever I did the calibration curves, so that was a little concerning for me. So I would like to go back and quantify, compare that to the QFL percentages that we get, which could tell us even more about the sediment sourcing in the depositional area. So I really feel like I really think that it has something to do with homogenizing the sandstone samples. And I think once I can get that down, it will give us out some better percentages as far as the IR analysis. I also want to collect spectra of clay minerals like kaolinite and morellinite, for example, because those are typical in depositional areas near shore faces. So I would like to thank UNAVCO, the Natural Science Foundation, for this opportunity. And as I mentioned earlier, Dr. Edgardo Pujols, who is my current and also a good friend of mine, he's a good mentor, Dr. Shin, who is also a current mentor of mine, and all their hard work that they did. My previous mentor, Dr. Julio Leiva Lopez, his contribution are these samples, and my communication mentor, Ann Bedrow. So, any questions? All right, thank you, Haley. I'm back. Oh, thank you, Andy.
So a lot of these clay-forming minerals, like the montmorillonite, for example, are really important contributors to the surface regolith on small asteroids, which are also pulverized by constant micrometeoroid bombardment down to very, very small sizes. So their spectral properties are of intense interest right now, particularly at small sizes, because the light scattering models that we use to infer the composition remotely tend to break down around small particle sizes. So I was curious, how small are small when you're generating these spectra? What is the size of the particles you're generating?
So that's a very good question. Typically what you would want to do IR, because whenever you're homogenizing the sample, you want the smallest grain size as possible. These clay grain sizes are the best is to get it below 5 microns. So really the smaller you get, the better. The clearer the spectra is, the less noise, and you can see the bonds, the chemical bonds, a lot better. So actually, what you're talking about, do you know how small these grain sizes are?
You can get down, 5 microns is a typical fine on the surface of the moon, but you get like hundreds of nanometer scale particles. Right. The rinds of olivine grains are loaded with nanometer scale iron grains. So.
Okay, so I don't know how low actually you could get. I know below 5 microns is really good for less noise, but I don't know if getting down to the nanoscale, what would happen. I would have to look into that, but that would be a really interesting question to look into, actually. Yeah.
Other questions for Haley? Anyone? Oh, thank you.
So you said, Haley, that you're still working on the quantification, but ultimately when you get it quantified, you're trying to compare with the QFL. So you've got the spectra for Q and you've got the spectra for F. So if it's not a Q or an F, are you then, for comparison, saying it must be an L? Because the lithic is not a monomineralic.
I see what you mean. So I'm not sure entirely what I would need to compare it with then. That is something I need to look into as well. But our interest in the study was to look at the finer particles in the L, in the lithics. That's what we want. And because that will give us more of an idea, like this study actually showed the OH bond, you know, which would fall into the lithics category because it's too small to see, or it could be combined into another rock sample. So I would have to look into it, but I think that is actually one of the biggest part of this study, was to actually look into that L and see what minerals are in that L, so we can build a better picture of what was going on. Did that answer your question? Okay.
Haley, I know I visited you midsummer. How many samples did you prepare? So
Okay.
many, but like approximately, I don't know.
Okay, KCl pellets or actual like minerals and samples?
The pellets.
Oh my goodness. Okay,
Just
so
a rough
for
ballpark.
a rough estimate, I don't know, but I will tell you for each mineral, I ran probably about 8 KCl pellets, so 8 times 5 is 40.
Okay.
And then for the samples, probably around, there's 2 or 3 each, so 12 of the samples. To give you an idea, it takes about 30 to 45 minutes to make each sample. It takes like 1 or 2 minutes to run the sample, and it's a lot of hard work. When you do the mortar and pestle, you're having to break up the actual potassium chloride crystals, and it's hard. It's fun, but yeah, it's time consuming, and each pellet takes about.
That's a lot of work.
It was a lot of work.
All right, thank you, Haley. Let's give her another round of applause.